So good morning, everyone. My name is Francesco Petruccione, and I have the pleasure of chairing this first session of today. Yeah, and yesterday we had a fantastic opening of the workshop, and I think we need to all thank Vinayak for the really excellent job in getting the testimonials, yeah, and the messages from our three guests of honors that were two of the co-authors of the famous paper and family members of Sudarshan, who unfortunately is no longer with us these days. Yeah. So this morning we have again a very nice program. Yeah. Our first speaker is Daniel Burgarth, who is joining us from Australia. Good morning, Daniel. Or good evening, Daniel, because it's probably dinner time in your part of the world. Yeah. And he will be speaking about the Quantum Zeno Effect, which was one of the big achievements of Sudarshan, as we heard yesterday in the memories shared with us by his wife. Yeah, Daniel. Before I ask you to start, I just wanted to remind the speakers of today's sessions and maybe some of the speakers of yesterday's to please, if they are happy with it, to share the slides of the presentation so that we can post them next to the of the conference. And please, if you're not a speaker, maybe mute yourself while during the presentation. Otherwise, I will force mute you from my side. Yeah, Daniel, please, you're welcome to share the screen and start your presentation. And you have half an hour. Yeah, and we still have 5 minutes for questions and to move on to the next talk. Thank you.
Perfect. Thank you so much. Thank you so much for inviting me to speak here. It's a great honor, and thank you also for giving me the opportunity to give the first talk. But I'm sure it's just because it's 8 o'clock here already. So I do apologize that I couldn't make it yesterday either, because it was just a little bit too late here in Australia. But I will try to stay around at least until lunchtime after this talk. So this is work collaboratively with Paolo Facchi and Saverio Pascazio. I think Paolo I've seen in the audience here as well, at Bari University, and with Hiromichi Nakazato and Kazuo Iwasa at Waseda University in Japan. The title of the talk is the Quantum Zeno Effect and its applications in quantum control. So quantum control being my main area of research. And of course, Quantum Zeno Effect being one of the great achievements of Sudarshan. And so I thought it's interesting to make a connection between the paper that brings us all together here that we celebrate, and the other paper that was already mentioned yesterday, which also involved Sudarshan on the Zeno paradox. And superficially, you might say that there might not be much of a connection because this is about noisy generators, whereas this is about measurements. But of course, if you are familiar with open quantum systems, you know that there are connections between measurements and noise. And indeed, the connection that I want to elaborate today in this talk is Quantum Zeno Dynamics. And we will see in this talk there are different manifestations, physical manifestations of Quantum Zeno Dynamics. And one of it is indeed by GKLS generators. So to give away the connection already, you can induce a Zeno effect by a strong damping, and that shouldn't surprise you if you're from this area. And I want to elaborate a little bit the relevance of this connection and its applications to quantum control. By the way, if you have questions or comments, please feel free to interrupt me at any time. So let's start with the Quantum Zeno Effect. So on a very superficial way of introducing the Quantum Zeno Effect, you probably know this English saying that a watched pot never boils. And more precisely, if we go to a finite dimensional Hilbert space, it's very easy to explain what the Quantum Zeno Effect is about. Let's look at the survival probability. So we initialize a system, a finite dimensional quantum system in some state. We evolve under some Hamiltonian. And we ask, what is the probability, so modulus squared, to find our system in the same state again after an evolution of a certain time. And because it's finite dimensional, we can just do a Taylor expansion of the exponential function here. And we can take the modulus squared. And what we will see is that the decay of the survival probability here is quadratic in time. And the time scale is essentially given by the variance of the energy in the given state that we start with. So if we plot this, we see something like this. Now, what Sudarshan already noticed is that when you perform a projection, and for simplicity, let's consider the projection where we ask the system, are you still in the state in which you started? That essentially resets the clock. If the system says yes, and we're going to assume for the moment that the system says yes, then the evolution onward will be as if time has been reset to 0. So as if the system just started, and the evolution will again be quadratic. And so if we repeat this measurement, we will modify the decay that originally looks like this, modify it to something that might look like this. And you can see then, if you make the time scale of your measurement shorter, you will start stabilizing your system. And in the limit of infinitely short time scales, you will indeed freeze the system. And so this was the reason, in analogy with the Greek paradox, to dub this the Zeno effect. And yeah, so this was worked out in this paper, and there's a very nice review also by Saverio and Paolo, which talk a little bit about the history of this. So this already demonstrates, and that I guess was the purpose of Sudarshan's work, the active role of measurements in quantum theory. And what you see here is, in the particular case where this projection is a rank 1 projection, you are completely freezing the system. But this gives some freedom to ask what happens when we are not having rank 1 projections, but higher rank projections instead. Indeed, Sudarshan already considers this case, but really it's fully worked out only in Paolo's and Saverio's work here. What happens in this case when this projection is more general? And you can just do a Taylor expansion again on the exponential, and you can re-exponentiate, and you will see that in the limit of n goes to infinity, the dynamics, the original dynamics given by a Hamiltonian H, is modified by a dynamics given by a Hamiltonian PHP. So this is the magic formula for this talk. This is known as the Zeno Hamiltonian. So if you are measuring with rank 1 projection, you freeze everything, but if you're with higher rank, you don't necessarily freeze everything. In fact, what happens is that the original dynamics gets constrained into the subspaces corresponding to the measurement and the complement of the measurement, and inside these subspaces you get a modified dynamics, the Zeno dynamics. So as I said already, if you have rank 1, you get a full freeze. If you have a full rank projection, of course, you do nothing, and in between you get the Zeno dynamics. And this, you can already imagine, is a valuable tool for quantum control because it allows you to change dynamics, and that is what quantum control is all about. But before I explore the connection with quantum control a bit further, let me talk about an interesting experimental realization of Quantum Zeno Effect and Quantum Zeno Dynamics done here in 2014 in Italy. So what they considered is a 5-level system. I'm not explaining the physics of it, but I'm just looking at it from an abstract perspective. They have a 5-level system given by some angular momentum states going from -2 to +2 here on the M quantum number. And what they want to do is they want to perform repeated measurements on this level here. And the way they do it is by pumping a transition to another level, and then from that level pumping another transition to a meter stable level, which is then led to some detection of a photon. And so if they don't perform anything here, if they don't perform these measurements, they just get a 5-level quantum dynamics. So for example, here, this is a particular population here, which starts at 1 and goes down and comes up again. But there's also population at another side. So this one here is the m equal to 2 state. This is m equal to 1 state, m equal to 0 state. So as we go down here, we start exciting m equal to 1. We start exciting m equal to 0. So you can imagine this like a movement back and forth. This is just angular momentum dynamics, essentially. Now they switch on the measurement. And how do they do that? Well, as I explained, they first bring whatever is here, the population is brought over here and then brought to a meter stable level where it decays and excites a photon. So this is the pulsed scheme here. And what effectively happens is that because you're measuring this level strongly, it no longer can take place in the dynamics, it becomes frozen, but the other levels can still move. And so essentially you're splitting your 5-level system into two-level systems on which you get coherent oscillations. And of course, this is what they saw, the beautiful coherent oscillations. So all this complicated cosinus spaghetti here has turned into essentially just a cosine function or a sine function, depending on what you look at. So the inverted green triangles here are the data of this experiment. Now, one day, the PhD student who did this experiment forgot to switch off the pulse shaper here. So what happens is that instead of just performing one measurement, waiting a bit, performing another measurement, waiting a bit, they just perform a continuous pulse that brings population from here to there and population from here to there. So it's a continuous measurement. And they measured these points, the balls. And you see the balls are exactly where the triangles are. Another day, this PhD student seems to be very forgetful. They forgot to switch on the measurement. So they didn't actually apply a measurement at all. They just applied the unitary here that corresponds to this coherent driving of this transition. And they see the triangle data, which is again the same. And then the other day, they even forget to switch on and off the pulsing of the unitary. They just apply a constant unitary, but no measurement. And they see the squares. And again, they see the same data. So this is what I mean with different manifestations. So these are different physical ways of implementing Zeno dynamics, but they all give exactly the same limiting dynamics. Now, I described this as a forgetful PhD student, but of course, the story is that there were already theoretical papers that would predict this. So there's, of course, the original paper by Misra and Sudarshan. For the pulsed unitary case here, there is dynamical decoupling and also work by Paulo here, connecting dynamical decoupling to the Zeno effect. Then the case where you just apply a constant unitary or constant Hamiltonian is the strong continuous field case here, which was also worked out by Saverio and Paulo. And then the strong damping and continuous measurement case, where we constantly drive the transition to some metastable level, and so we constantly get decay, was worked out by Zanardi, and there's also other interesting work by Victor, for example. And this is the case really that connects us with the other work of Sudarshan, because this is really something that is about GKLS generators. Okay, so our contribution to this story is that we wanted to generalize this to CPTP maps. So instead of just kicking with unitaries and projections, we wanted to kick with CPTP maps. And we wanted to unify the story of a strong continuous field and strong damping, which look mathematically a little bit different. And we did this by an adiabatic theorem, which gave us a unified theory of the Zeno effect of all of these different effects through one proof of an adiabatic theorem. And so I will just throw the formulas at you, because we're going to need one of them for what comes afterwards. So these are the graphical representations of these data points that the group observed. There's also a new point that wasn't experimentally measured yet, but that we're predicting. The first one here is the one that you really should pay attention to. So this is the case where you have one generator that might be a Hamiltonian or might be a GKLS generator, and you have a strong term. So the green terms here are the strong terms. And in the limit of large gamma, this exponential can be approximated arbitrarily well by this exponential here, where you get the strong part unmodified, but the weak part, the blue part, becomes xenophied. It becomes an effective Zeno generator. And we will see in a minute how this looks like. We can do the same thing, although it's not so relevant for the rest of this talk, with CPTP kicks, where again we get the blue part, the weak generator, turned into a Zeno generator. or generalization here with multiple CPTP kicks or multiple unitary kicks. And again, the weak part, the blue part here, is modified into the Zeno generator. So just for completeness, these are all the definitions here. I'm not going to explain them, but I'll just explain this one here because that's the one that we need. So we write the strong part in a spectral decomposition in terms of spectral projections and nilpotence. And then the weak part, this L here, gets projected by the projections that correspond to eigenvalues on the imaginary axis. So it gets projected by the part of the GKLS generator that does not decay away. And this dynamics takes place on a space that is described by another projection, P phi, which is the peripheral, that's hence the phi, peripheral projection, which is given by the sum over all the spectral projections of the strong part over the imaginary, over the part that doesn't decay away. Okay, so in the strong gamma limit, this defines what survives, and on the space that that survives, we get this Zeno dynamics that I talked about on the previous slide. So what I would like to do next is to explain to you a little bit how to use this for control. So control theory is maybe not so familiar to some of you. So let me just spend one slide on introducing in a non-technical what is, from my perspective, at the heart of control theory, and that is non-commutativity. So just to give you an analogy that I took from this book by Nelson, we're going to look at driving a car. So this is a theoretician's picture of a car, and a car has two elementary operations. If you're not familiar with driving, you can have the steering wheel and you can drive backwards and forwards. And the first question you would ask as a control theorist is whether these two operations are commutative. The answer is of course not, because if they were commutative, you could interchange the steering with the driving, and you could do all the steering in the morning when you start using your car, and then afterwards only do the driving, right? So that doesn't work. And so if we want to quantify what is the commutator of steering and driving, what we can do is a little thought experiment where we steer the wheel to the right and we drive a little bit forwards, and we steer the wheel to the left and we drive a little backwards. Since we've undone everything that we did, if they were commutative, we would do nothing. But if you can see, and if you're driving, you know this very well. I don't have a license, so I don't know this very well, but I guess you do. So you actually effectively rotate the car. And so then you can ask, well, what about rotating and driving? And of course, that also does not commute. So if you drive a bit, you rotate, you drive backwards, and you rotate backwards, you will move sideways. And this is what you use when you park your car. This is parallel parking, essentially. So if you can drive and slide sideways, then you can, of course, move in any direction. And so this is how a control theorist would try to understand driving a car. And the tools are, of course, Lie algebras, Lie groups, Trotter theorems, differential geometry. But the point here is that this non-commutativity also lets us understand how and where we can drive in a Hilbert space situation. So this is what we're going to apply now to the Quantum Zeno effect. And the central question that interested us was, how does the Quantum Zeno effect or the Quantum Zeno Dynamics affect commutativity? In particular, if you have two Hamiltonians that commute, and you then modify the system by projecting it, does the projected system still commute? Right? This is a simple mathematical question. If two Hermitian matrices commute, is it true that for some projection, the projected matrices still commute? And the answer is no. And we found a particularly stark example, which is a little bit contrived, but I'll spend one slide explaining it, which showed us how Zeno is actually really useful for control. And this is an example that involves n qubits. So here's my n qubits, and the two Hamiltonians that we have are Pauli X on the first qubit, Pauli X on the second qubit as the first Hamiltonian. And the second Hamiltonian is essentially a Heisenberg spin chain. these two Hamiltonians commute. We constructed them so that they commute. And in order to make them commute, we had to cheat a little bit so that this H2 is not only a Heisenberg spin chain, but there are two cheating terms as well. And if you need to know what they are, it's a kind of three-body interaction between the first three qubits and another Pauli Z on the third qubit. This is not so important for the story, but it's important for the proof. So if you switch between these two Hamiltonians, because they commute, the time evolution operator just splits into the integrated control pulses, and the dynamics is rather trivial. But the question which we were asking is, what happens then if you perform a measurement on a single qubit? Let's say we perform a measurement on this qubit 1 up here. We chose a measurement that has this property here. So it's essentially a measurement that goes on the Bloch sphere on some diagonal. It has overlap with all three Pauli matrices. And so if you perform the Zeno effect for this projection here, you will see that essentially the first qubit becomes classical, becomes decoupled, and points just in this direction of the projection. The rest becomes a normal Heisenberg spin chain, and the original H1 becomes a local driving, edge driving on the spin chain. And this is good because for this case of edge driving, there are previous results, and I also worked in that area, which show that this is actually universal for quantum computation. So this is really a maximally non-commutative example in the sense that the projected Hamiltonians do not commute. This answers the first question from the previous slide, but they commute in such a bad, they don't commute in such a bad way that they generate actually the whole set of Hamiltonians on n-1 qubits, which means that the system mathematically is universal for quantum computing. Now, this is a very contrived example, but what you can then prove is that this happens actually in almost all cases. And so it's a rather strong effect. So this was a result here in 2014. But recently there has been actually experimental demonstration of this at Technion University in Israel, where they showed that they can do this with two qubits, actually two transmons. Transmons, as you know, are not just two-level systems. You can use higher levels. I'm not going to explain the experimental setup here, but I'll just explain what is the original Hamiltonian and what is the effective Hamiltonian under the Zeno effect. So what they considered is a three-level system. They looked at the three levels for the first transmon and two levels for the second. I'm going to call them 0, 1, and 2 for the first and 0 and 1 for the second. They looked at this particular projection. So it excludes a particular level here, the level where the first transmon is in level 2 and the second transmon is in level 1. So this is a non-local projection. You can't just decide by looking at one of the transmons whether the system is in this state. And then the driving, they did a Rabi oscillation on the first qubit. So this is a local driving. And so what you have here is this interesting effect that you have local driving, but non-local projection. And when you interplay them in the Zeno limit, what you will get is a non-local Hamiltonian. You will get something entangling. So to see this, I'm going to rewrite the identity here as 0 plus 1. And I'm going to multiply out into these four terms. And when I project them, these two terms here have a 2, 1, and so they disappear. And what is left with is essentially this guy here, which looks similar to where we started, but it no longer has the 1 level. And so it's essentially a conditional evolution on the first system, depending on the second system being in the ground state. So this is an entangling gate. And what they did in this experiment is to use this entangling gate to create essentially something like a C0 or a C phase gate more precisely, so a C0 in a different basis. Okay, I'm going to skip this slide in the interest of time. You can ask me later how good this was, but the outcome, experimental outcome, is that it works okay. It's not fantastic in terms of, if you compare with the latest Google experiments, but if you compare with results a few years ago, this is actually pretty good. And the main result is that this combination of the two results by Sudarshan actually works. And so what I should have mentioned is that they don't actually perform projective measurements in the system, but they actually implement something that is more like a strong GKLS generator. So they drive a transition that is pumping population out of the system, similar to the experiment in Italy that I mentioned in the beginning. So it's really important that we have a Zeno effect here that works with GKLS generators. But, and then this brings me to the end of this talk, and I think this is probably the most interesting thing in the context of this workshop, because it brings together the structures of GKLS with Zeno Dynamics. There is some friction between these things. When you put them together, when you put the two papers by Sudarshan together, there is some interesting things happening. And I don't know the full story of this yet. So this is actually work in progress. So I explained to you that when you have this strong damping generator, essentially the weak generator here that you don't scale with gamma gets projected by these projections. Now in the Hamiltonian case, this is rather simple because your Hilbert space gets split into orthogonal projections. And so if you project a Hamiltonian with orthogonal projections, you get a Hamiltonian. But here we are actually in superoperator space. These projections are superoperator projections, and they're not necessarily CPT projections. They are not necessarily physical. And so we are sandwiching here this Lindbladian or GKLS generator between these projections, and we shouldn't expect that the outcome LZ is CPTB. And in fact, let's define this object here, lambda of t. Lambda of t is the limit evolution where I assume for simplicity that this gamma 0 here has no support on p phi, so it just goes away. But you can also do it in other cases. So this limit evolution is CPTP, right? And this is because it is a limit of a CPTP map for large gamma. And in fact, it has a kind of semigroup structure. But if you evaluate it at 0, you don't get the identity map, but you get this p phi. And this means we can't apply the GKLS theorems straight away. And what we find is that this e to the LZT, this Zeno generator here, this effective Zeno generator, is indeed not always CPTP. Sorry, this evolution is not CPTP, and the LZ correspondingly is not of GKLS form. And this is something that provides a little bit of interesting friction between these two results. One is about projections and one is about damping. And if you project damping, then you break the validity of the structure. Now, what you can do is you can use like the C-star algebraic results, which of course become rather simple for finite dimensions, but they are still relevant, by Christensen and Evans, to see that such an evolution here has to have a valid GKLS generator nonetheless. So there must exist a GKLS generator such that you can replace this e to the LZ p phi with e to the GZ p phi and have equality here with this being valid. And this is just because on the range of this p phi, you essentially have a C-star algebra. And on the C-star algebra, this becomes a real CPTP semigroup, and you can then use this result to find a generator. But the interesting thing is I don't have a clue how to do this. I don't have an idea how to construct from LZ my GZ, or maybe even modify this formula in the first place in such a way that this is always physically valid. So I'm hoping that the next speaker has some good answers to this, because I think it might be related to some pseudo-inverse. And Darius has some nice ideas of how to use some freedom of the pseudo-inverse to explore this. But at the moment, I really don't know. Okay, so this brings me to my conclusions. so the one thing that I wanted to emphasize is that the Zeno Dynamics can be implemented by a variety of physical mechanisms, and this gives you some freedom in implementing it experimentally, but it's also interesting mathematically because it essentially shows some sort of adiabaticity in the system or some separation of scales. And these have applications in quantum control and quantum computation, and the experiments are just catching up with that now. One example that I emphasized today was the result by the Technion group. And we connected two results by Sudarshan, but not without friction. Thank you so much for your attention.
Yeah, thank you very much, Daniel, for the very clear and interesting talk. We really appreciate your effort to connect it in the general context of the workshop. And also thank you very much for finishing on time. So we still have 4 or 5 minutes for questions. Please, I see Darius unmuted himself. Would you like to ask a question, Darius? Or answer the question that Daniel asked you?
I would like to thank Daniel for a very interesting question. I promise to think about this. No, it's, you know, it's very, very interesting structures that you have a kind of gauge freedom. And using this gauge freedom, we can always pick up a proper GKLS generator, right? Very interesting.
That's right. We know we can, but we don't know how.
I agree. No,
and so, I mean, in some sense, when you look at this formula, it looks very beautiful mathematically, and it looks like it should be the right one, but it's not really physically.
But do we know anything about uniqueness of this generator?
I would guess that on the support of on the output of this CPTP projection here, it should be unique.
I see. Okay.
But outside, you can basically do everything. We have some examples also in the paper where we change it a little bit to bring it back into this form, and then everything is okay by basically adding terms that get annihilated by this projection.
Oh, beautiful stuff.
Thank you.
Excellent. Thank you very much. Are there further questions for Darius?
Or for Daniel?
Sorry, sorry. I was looking at the program to read the title of Darius' talk for the next step. Sorry. Are there further questions for Daniel? Okay, nobody seems to raise their hand or start talking. So Daniel, thank you so much. It was really an interesting talk. Sorry, please. I'm not sure who is talking, but please ask.
Right, so my question is, so in the example where it was shown that, okay, actually I forgot the exact detail. Basically what I see is happening is that you perform a measurement. I mean, in one of the examples in the talk, you perform a measurement on a single qubit. And I mean, then the way that the measurement is performed, you get universal dynamics. So suppose I perform a stabilizer measurement on the single qubit instead of, let's say, a non-stabilizer measurement. Then, I mean, the theorem, that would also still be an example for, you know, the theorem, right? I mean, sure, this is about the power of, you know, Zeno control, but as such, you know, the former question of the commutativity of the dynamics, so that is still satisfied even for stabilizer. I mean, so that it is not commutative even for stabilizer single measurements generally. That is also true, is that right?
So you want to replace this projection here, if I understand you, with a, let's say, sigma x projection, a projection in the x direction or something like that, or z direction? Or what do you mean with stabilizer projection?
So yeah, I mean, my assumption is that you get universal this thing if you, let's say, perform, you know, a measurement which is not a stabilizer one, because ultimately then you're, I mean, if you like just perform a stabilizer measurement, then, you know, ultimately you're just doing a stabilizer operation. So that cannot give you full dynamics, right?
So you're thinking about something like measurement-based quantum computation?
I mean, yeah, I mean, so I mean,
what do you mean with a stabilizer measurement?
a stabilizer measurement, as in, you just measure in like the eigenstates of like stabilizer operators. You have an X, you have Z, you have Y for all your qubits.
Yeah, it depends on your system. There are particular systems in which case the measurement does not induce universality, and we're not claiming that it does in those systems, but it does almost always, in the sense that you can slightly rotate your system, and of course then it's no longer made out of stabilizers, and then it induces universality as well.
Yeah, sure. But suppose if you actually make a measurement on just the stabilizer, then the earlier theorem of commutativity, I mean, sorry, not commutativity, anti-commutativity, that still holds true, right?
It's an interesting question, but I don't know the answer straight away. So maybe connect with me in the chat and we can discuss a bit.
Oh, sure. Okay. So I'm actually using someone else's account to ask this question. So I'll comment with you. I mean, I'll connect with you in the chat afterwards with a separate name.
Okay.
Thank you.
Thank you.
Perfect. Then Daniel, thank you very much again for the excellent talk. And maybe I can ask Usha to communicate with Daniel in the chat, because otherwise we start running out of time.
Okay,
and we have
fine.
many more talks today. I hope you don't mind. Yeah. Thank you. Thank you very much. Okay. So